Our problem is, in an RCL circuit, R, the resistance, is 275 ohms. C, the capacitance, is 5.12 microfarads. L, the inductance, 1.38 henries. At a frequency of 75 hertz, the RMS current is 0.233 amps. The question then is, what is V naught? Let's approach this in a very, very general way, a very similar way that you could approach any type of physics problem, essentially. That is, let's think about what do we want, and what do we know about that thing that we want. And if we're not given the things we need, we'll just keep going and figure out, well, what do we need to get that? What do we need to get that? What do we need to get that? That is basically a very, very general approach which can be applied to just about any of these types of physics problems. What are we looking for? What is V naught? That's what we want. We're looking for V naught. What do we know about V naught? Let's be careful. We're talking about an RCL circuit. We're not talking about a resistor by itself. We're not talking about a capacitor by itself. We're not talking about an inductor by itself. What do we know about the voltage amplitude for an RCL circuit? Well, we know the voltage amplitude is Z times I naught, the impedance times I naught. This would be R if we had a resistor by itself. It would be XC if we had a capacitor by itself. This would be XL if we had an inductor by itself. But for all three, an RCL circuit, it's Z, the impedance. We also know that V naught over root 2 is VRMS. Well, in this case, to find V naught, we need, what do we need to find V naught? We would need Z and I naught. In this case, to find V naught, we would need VRMS. Well, let's go with the first one. Let's just say we're going to use this one. Using this one, you will see is a similar fashion. To find V naught, we need Z and we need I naught. Are we given Z and I naught? Well, no. So what do we have to do to find those? To find I naught, what do we know about I naught? Well, IRMS is I naught over root 2, or I naught is root 2 times IRMS. But we do know IRMS. Excellent. We can use IRMS to find I naught. Now the only thing we don't know is Z. What is Z? How do we find Z? Well, what do we know about Z? We know that Z is equal to the square root of R squared plus XL minus XC quantity squared. So here. To find Z then, we need to know, well, let me ask you, what do we need to know to find Z? We need R, we need XL, and we need XC. Well, R, we know R. We've got R. So what else do we need? We need XL and XC. We don't have those. How do we find those? Well, we know that XL is omega times L. We know L, but we don't know omega. How do we find omega? Well, what do we know about omega? We know omega is 2 pi f, but we do know f. So we can use f to find omega. What do we know about x sub c? We know x sub c is 1 over omega c. We have c, and if we find omega for x sub L, then we can use it for x sub c. And there we go. That is a way of finding everything we need to get back to our final question. And that's how we'll proceed. And that's how you should essentially proceed anytime you get a problem like this, or essentially any kind of physics problem. Think about what you're looking for, and then ask yourself, what do I know about that thing? What equations? Typically, mostly equations, that's usually what we'll be doing. Sometimes not everything will be an equation, and you'll have to think about things a little bit differently. But for the most part, we're talking about equations. What are you looking for? What do you know about that thing? In other words, what equations have you ever seen that used that thing, but let's be very, very careful, for that particular kind of problem. Make sure that because we use variables so often all over again, make sure that you're talking about the thing you're actually looking for. Just because you say you want, well, I'll give you an example from 1111. Let's say you're asked for W. Well, what do you know about W? Well, is W the weight? Is it the work? Is it a watt? be very careful. You've got to make sure that what you're looking for is actually what you want to be looking for. So we've done this one. Let's stick the numbers in and see what we get. Working from the bottom and going up, we need to find omega, which is 2 pi f. Well, omega, 2 pi f is 2 pi, and we know f is 75 hertz, so that is 471 radians per second, or inverse seconds. There we go. We know xc is 1 over omega c. xc, 1 over omega c. Omega, 471 inverse seconds. C, 5.12 microfarads times 10 to the negative 6 farads. 1 over that gives us 415 ohms. XL is omega L. Omega L, 471 inverse seconds times 1.38 henries, or 650 ohms. We know Z is root R squared plus XL minus XC squared, or R 275 ohms squared plus XL, which we found to be 650, minus XC, which is 415, quantity squared. Be very careful when you do this out. You might want to take the 650 minus 415, evaluate that, square that, then add the 275 squared, evaluate that, then take the square root. Make sure you are careful with your order of operations. What you end up with is 362 ohms. Then we know that I naught equals square root of IRMS. IRMS 0.233 amps, or 0.330 amps. And then we don't need to do this one up to here. V naught equals Z I naught. V naught equals Z. Z we found to be 362 ohms. I naught 0.330 amps, to leave us with V naught 119 volts. And that's what we were looking for. Very, very good. Let's try sticking some numbers in another problem. This problem is going to be a little bit different than the last one, and we'll see how it is different as we proceed. The problem is, an RCL circuit has a resonant frequency of 1500 hertz. Off resonance, in other words at another frequency, not the resonant frequency, X sub C, the capacitive reactance, is 5.00 ohms, and X sub L, the inductive reactance, is 30.0 ohms. And then the question is, what are L, C, and omega? Again, let's think about this. What are we looking for? We're looking for L, C, and omega. What do we know about L, C, and omega? But rather than writing down every possible equation where we've seen L, C, and omega, let's focus on those that will use the information that we're given. Now, what are we given? We're given the resonant frequency. We're given a capacitive reactance, off resonance at a different frequency. And we're given the inductive reactance, again at a different frequency, but the same frequency at which the capacitive reactance is calculated. So what are those things? Well, we know the inductive reactance is omega L, and there's L, that's what we're looking for. We know the resonant frequency, but let's just be a little bit careful. What are we given here? We're given a resonant frequency, but keep in mind, we have a resonant frequency and a resonant angular frequency. Sometimes when an angular frequency is meant, it's just called the frequency. You've got to be a little bit careful. Do they mean the ordinary frequency or the resonant frequency? Well, you can tell if you look at the units. The units here are hertz. What does a hertz mean? A hertz is a cycle per second. This must be the ordinary resonant frequency, F naught, not omega naught. So we know that omega naught is 1 over root LC, and omega naught is 2 pi times F naught. So here's F naught. That's the quantity we're actually given, which we can use to determine omega naught. And then given omega naught, we can figure out, well, maybe not what either of those are, but we can figure out what the product of L times C is, what that product is. And then, what else? Well, we're given the capacitive reactance. The capacitive reactance we know is 1 over omega C. Well, let's just think about that. Let's just stop there for a second. We are given 3 quantities, 1, 2, 3. The resonant frequency, the resonant ordinary frequency, a capacitive reactance, and the inductive reactance, And we're asked for three things. Well, here we have essentially three equations. Putting these together to make one, we have three equations. We've got three equations with three unknowns. We can manipulate those to figure out what we're looking for. It's going to take a little bit more algebra than we used in the last problem, which was basically find this and it gives you this. Once you have that, you can find this. Once you have that, you can find that, etc., etc. We're going to have to manipulate them just a little bit more this time. Let's take a look. We know that omega naught, the resonant frequency, is 2 pi f naught. Omega naught is 2 pi f naught, and we know f naught is 1500 hertz. So omega naught is 2 pi times 1500 hertz, or 9425 inverse seconds, 9,425 inverse seconds. We were given this in 4 sig figs, so we've got 4 sig figs there. We know that omega naught is equal to 1 over root LC. So we know that 1 over root LC equals 9425 inverse seconds. Taking the inverse of that and squaring it, we have that LC equals 1.126 times 10 to the minus 8. And what are the units for L times C? Well, you can put the units in here, but you know it's got to be an inductance times a capacitance, a Henry Farad. There we have LC equals 1.126 times 10 to the minus 8 Henry Farads. We also know the capacitive reactance for a different frequency. Actually, I wrote down the inductive reactance. We know the inductive reactance at a different frequency is 30 ohms. We know X sub L is omega L, and that's 30 ohms. And the capacitive reactance at that same different frequency is 1 over omega C, and that is 5 ohms. What do we have? We've got three equations. LC equals that value. Omega L equals that value. And 1 over omega C equals that value. We've got three equations and three unknowns. What we have to do is just manipulate them to try and figure out how can we get each one all by itself. Well, there are different ways you can do that. The way I did it was I took omega L and multiplied by 1 over omega C. Omega L times 1 over omega C is, omega L is 30 ohms, and 1 over omega C is 5 ohms. I multiplied those and got 150 ohms. But what is omega L times 1 over omega C? We know the omegas cancel, and that leaves us with L over C. I then took L over C, which is 150 ohms, and multiplied by the product of LC, which is 1.126 times 10 to the minus 8 Henry Farad. So LC times L over C is 1.126 times 10 to the minus 8 Henry Farads times 150 ohms, which gives us 1.69 times 10 to the minus 6. And what do we get on the left side? Well, the capacitance cancels out, and we're left with L squared. What are the units on the right side? Well, it's a Henry Farad ohm, which we know has to be an inductance squared, so it's just a Henry squared. Taking the square root leaves us with the value for L. We've got L all by itself, which turns out to be 1.30 times 10 to the minus 3 Henries, or 1.30 millihenries. Then going back to one of the previous equations, and the one I used was this one. We know LC is equal to this, so C must be this divided by L. C is 1.126 times 10 to the minus 8 Henry Farads divided by L, and L we now have 1.30 times 10 to the minus 3 Henries. The Henries cancel, and we end up with C equals 8.66 times 10 to the minus 6 Farads, or 8.66 microfarads. What's omega? Well, come back here. We know omega. Omega L is 30 ohms, so omega is 30 ohms divided by L. Omega 30 ohms divided by L. We have L. Putting that in, and we get omega is 2.31 times 10 to the 4th inverse seconds. Well, that was a little more difficult, but not that much more difficult. It just took a little bit more algebra and manipulating the equations. Excellent. Well, I hope that was interesting, and I hope that was fun. Like I said last time, I really do like this stuff. I hope you enjoyed it too. I'll see you next time.